Hello! Today we will solve a couple of problems concerning multivariate normal distribution. First problem is going to be to find the probability density function of a bivariate normal distribution. So, if we have a bivariate normal distribution, we mean that our vector x is actually a vector that contains two elements, x1 and x2. So, our random variables x1 and x2. We can find the probability density function by the definition of multivariate normal distribution. So in the definition we had how does the probability density function look like. So there we need to determine determinant of our covariance matrix and inverse of covariance matrix. So here we are missing to the power of -1. Both are easy to compute. Let's say for the determinant of the covariance matrix, on the main diagonal we have sigma 1 1, sigma 2 2, so we need to multiply those two, minus what do we have on the other diagonal? Well, because it's symmetric matrix, in both we have square root of sigma 1 1 times square root of sigma 2 2 times rho or rho 1 2. So the correlation between our two random variables x1 and x2. When we multiply that and we arrange it, we get our expression here. Then what we also need to do is compute the inverse, so we can find it and just find the quadratic form. When we do that and when we multiply, we will get exactly this form here. So this is what we get, this times this. So the whole thing, this is our quadratic form. As this is simple inverse of 2 times 2 matrix, you might know already the form, so 1 divided by the determinant, okay, times a matrix that has elements. So if this is our covariance matrix, A, B, C, D, okay, then we will have here 1 divided by determinant times, and now D minus C minus B, A, if I recall it. Good. So you can always find that inverse and then just matrix multiplication, and in the end you get this expression. So this is our quadratic form. If you need to compute the probability density function for concrete values, so if you're given the variance and the correlation coefficient, you can just substitute. Okay, so for values 1, 3, 2, and 1, and minus 0.8, you can just substitute and rearrange the expression. So the probability density function is this, and the quadratic form is this part here. What I mean by the quadratic form is that this is actually a function of x1 squared and x2 squared. Let's go to the second problem, in which we have a multivariate normal distribution. We have values for the mean vector and covariance matrix, and determine if a couple of random variables that are in this x are independent. So now we can use theorems from univariate case or a theorem from a multivariate case to determine which of the random variables are independent. Let's see for x1 and x2. In order to see if they're independent, we need to look at x1, x2 covariance or the correlation. So we know that the covariance is 0 if and only if, in a case of multivariate normal distribution, they are independent. So x1 and x2 are independent. However, in our case, the covariance is -2, so we know by this theorem that they are not independent. So x1 and x2 are not independent. Let's see for x2 and x3. In this case, it is easy to see that the covariance is 0 from the covariance matrix, and then by the same, so it is true only in a case of a normal distribution. So covariance is 0 if and only if x1 and x2 or x2 and x3 are independent. In general case, only one implication stands. So if they're independent, then the covariance is 0. The opposite does not stand always. But in this case, when we have normal distribution, it stands. And how do we know that x1 and x2 have a normal distribution? Well, also by, for example, theorem number 1, any linear combination has one-dimensional normal distribution. So we can just take a linear combination 1, 0, 0. In that case, we have 1 times x1 plus 0 times x2 plus 0 times x3. So this is just x1, and it means that it has a normal distribution. So this is explanation how we got to this point. Then let's see if the partition x1, x2 and another partition that is x3. So if we have this vector and this random variable, okay, and we want to know if they are independent. So now, because we have two partitions, we cannot use the univariate case theorem, so we need to use theorem 4 that says that they're independent if and only if the covariance between those two random vectors is 0 vector. Okay, so let's see what is the covariance between x1 and x2. So what we need to determine, because we have here x1 and x3, so this is going to be our first element of the covariance, and the covariance between x2 and x3 is our second element of this vector. So what do we have? x1, x3 is 0, and x2, x3 is 0. Okay, so covariance between our two partitions is 0 vector. So by the theorem number 4, they are independent. Okay, let's see what happens if we have some linear combinations of some random variables that are contained in our original vector x. Okay, so let's say that we have x1 plus x2 divided by 2. This is one random variable, so it is one-dimensional. And another one is x3, so we can denote them as y1 and y2. What are we interested in? In the covariance. However, before finding the covariance, we need to determine if those random variables are normally distributed, or we can take this two-dimensional vector and prove that it has bivariate normal distribution in this case, and then we can use theorem 4. So first way is to prove that this one and this one have normal distribution. Okay, so one-dimensional normal distribution, and then just find covariance and see if it is 0 or not. Or prove that this y, so our vector y, has bivariate normal distribution, and then use theorem 4 to prove if they're independent or not. Let's see first this way, where we have a vector y, y1, y2, and we want to prove that it has normal distribution two-dimensional in order to use theorem 4. So first, what we need is to use a linear combination of those vectors. So this is our theorem number 2. So what it says is that we have a matrix, let's say C, okay, and the vector. Then this combination is going to have a normal distribution with particular mean and particular covariance matrix. Okay, so by this theorem, when we choose this matrix, so how did we choose it? Well, we know the first random variable has in constant near x1 is 1 divided by 2, same for x2, and 0, so we are looking at this random variable for x3. And the second column has 0, 0, and 1. This is how we actually get this matrix. And then just we have vector. So this one by the theorem number 2 has Bivariate normal distribution with these parameters. But we are interested only in our covariance matrix. So we need to multiply, because we know by the theorem we can also prove it. How does the covariance matrix look like? And from there we can see actually that our sigma 1, 2, so sigma 1, 2 in this case is covariance between y1 and y2, what we need. So it is this covariance is 0. Now we can use theorem number 4 and say that they're independent. Another way, as I mentioned in the beginning, is to prove that both of those are multivariate normal distribution, so one-dimensional, and just find the covariance. It is easy to find it as we already have covariances, but as this is multivariate case and multivariate statistical analysis, we will do it in this way more often. So to use theorem number 4 instead of doing it the simple way. Let's have another combination just to see how it works. So we have on the one side x2 and the another side x2 minus 5 divided by 2x1 minus x3. Okay, so first we need to prove that y1, y2, okay, same as in this case, have Bivariate normal distribution. So first we need to determine the matrix C. So for x1 we have 0, for x2 1, and for x3 we have 0. Here for x1 we actually have minus 5 divided by 2. So we look at the first one. Then x2 is 1 and x3 is minus 1. Then by the theorem number 2 we know that it has multivariate normal distribution, in this case bivariate normal distribution. We know how the covariance matrix looks like. We can compute it and see that actually the covariance is something different than 0. So by the same theorem number 4 we can conclude that they are not independent, this random variable and this random variable. So here you may ask to find a linear combination such that they are independent or similar, which does not differ from this method. You just need to choose such constants that this is 0. So this would be just simple solution to equation or similar. Let's go to the following problem, problem number 4. So this is an example for the alternative definition. So just to remember, the alternative definition tells us that if a random vector has a multivariate normal distribution, then every linear combination of those elements of that random vector has univariate normal distribution, and if the linear combination is non-zero, and the opposite. So if every linear combination, has a univariate normal distribution, then the vector has multivariate normal distribution. Again, this has to be non-zero linear combination. So if you put every constant to be 0, then obviously you get 0. So just to pay attention to that. In this case, we will show that we have two random variables with normal distribution, but their joint distribution is not bivariate normal. So because it's not every linear combination of x2 and x1 that have a univariate normal distribution. Okay, so x1 has a standard normal distribution and x2 has this kind of distribution. So x2 is minus x1 for these values and it is x1 for any other, so from the left and right of minus 1, 1 respectively. But first we need to find what is the exact distribution of this one. As I mentioned, it is a normal distribution, so let's just prove it. So as this x2 is in connection with x1, we want to use the, let's say, cumulative density function of x1. How are we going to do that? We can find a cumulative density function for x2 using x1 for every x. Okay, so what happens for x smaller than -1? So for x smaller than -1, by the definition of cumulative density function, we have that it is the probability that x2 is smaller or equal than that particular x. So because it is smaller than -1, we know that x2 is actually x1 because it is in this case otherwise. So we can just substitute x2 with x1. And by the definition of cumulative density function, we know that this is actually cumulative density function of x1. Take x from -1 to 1. Let's see what happens with the cumulative density function in this case. So by the definition, this equality stands. Okay, then the following equality we need to separate because of this part, we need to separate when it is smaller than -1, because in this case we have x1, and when it is between -1 and, in our case, x, because x is between those two values, because in this case x2 takes values minus x1. So, as I mentioned, in this case, by the definition of x2, we can just write x1, and in this case we need to substitute with minus x1 because x is, as we can see, x2 takes values between -1 and x, and in this case it is this value. This equality is just simple algebra because of minus, and in the end this equality follows from the symmetric, because x1 is a standard normal distribution and we know that it is a symmetric. So what does it mean? That if x1 is between -x and 1, okay, so it is depending on, so x can be any value from -1 to 1. Okay, so anything here. So say that actually our x is negative. For example, it is from -1 to 0. We can take any just to see an example how will that symmetricity work like. So if x is negative, then minus x is positive. Okay, so the area between -x and 1 will be this area here. Okay, because we have a standard normal distribution. This area, or this probability, so it is the same, is going to be equal if we take from -1 to x, because the distribution is symmetric. Okay, so this is 0, our mean, because of the symmetricity. This is the same if, for example, x is positive. Okay, so if x is positive, then it would stand again, this equality here. Okay, so this is by the symmetricity of a standard normal distribution, or in general normal distribution. And what we see here, that it actually goes to -1 and from -1 to x, so we can write it, because there are two distinct events, we can write it as x1 is smaller or equal than x, which is actually our cumulative density function of x1. Okay, and in the last case we can do the same. So we can separate it, so smaller, between, and larger than 1. Okay, this case we can again use this part, symmetric, so because x1 is symmetric, and prove what we need if it is not obvious as it is. When you substitute -x1, you actually get what you need. And then we get again cumulative density function of x1. So the cumulative density function of x1 is equal to the cumulative density function of x2, So it means that the random variables x1 and x2 have the same distribution, and in this case it is standard normal distribution. So we know that x1 and x2 both have standard normal distribution. Let's see, is the x1, x2, so if we have our vector x is equal to x1, x2, is it bivariate normal distribution? So let's check this. In order for it to be bivariate normal distribution, it needs to have any linear combination to be, so by the alternative definition, to be univariate normal distribution. So let's, for example, check this difference. You can take any difference or anything similar. It might be a little bit more complicated, but you would still get the same result. But let's take this one, x1 minus x2. Does it have univariate normal distribution? So if x1 minus x2 have univariate normal distribution, okay, then we know that the x1 minus x2 equal to 0 with probability 0, because if it is a continuous random variable, then the probability that it takes a point, exact point, is 0. Okay, so let's see what is this probability. So probability that x1 minus x2 is 0 is actually the probability that they are equal. Okay, and when are they equal, x1 and x2? Well, we know that they are equal, so for these values here. So for absolute value of x1 larger than 1. And this probability, because x1 is a standard normal distribution, so the probability that it takes values larger, so absolute value of x1 to take values larger than 1, is the area to the right one and to the left of minus 1. And obviously, it is different than 0. The exact probability can be computed, as this is a standard normal distribution, so either use a software or a table. So it cannot have a bivariate normal distribution because of the alternative definition. So again, if it was a normal distribution, then this probability would have to be 0. Let's see how can we use theorem 7 to prove what are the distributions of particular random variables that are linear combinations of our random sample. So in that theorem we had v1 and v2, and we mentioned when are they independent, as well as the joint distribution of that when v1 and v2. First, let's find the marginal distributions of v1 and v2 that are given. So v1 is given as this linear combination, and v2 is given like this linear combination. So by the theorem 7, because we have a multivariate normal sample, so all our random vectors come from this distribution, then we can find the marginal distribution of v1. So the theorem tells us not only that the linear combination has multivariate normal distribution, but it also tells us what is the mean vector and the covariance matrix of that distribution. So because in this case our mean vector is the same for every random vector, okay, then we can just substitute it as mu and sum all the constants. So by the constants we mean 1/4, minus 1/4, plus minus. Okay, so we have this sum. This is our sum of CJ, and it is 0. So our V1 has mean 0, so it is expected value of this random variable. It also, the theorem tells us what is the covariance matrix. So again, this is in the theorem. It has to be the same for every random vector. and the sum of squared constants, when you sum them, you get 1/4. So this is our covariance of V1. So this is how we can use that theorem to determine the distribution of a linear combination. The same way we can do that for this V2. Okay, and we get that it is actually the same. So mean vector is 0 vector, and the covariance matrix is given like this. And let's find the joint distribution. So the theorem 7 again tells us how we can determine what is the mean vector, okay, and what is the covariance matrix. The mean vector can be obtained easily because we know the mean of v1 and v2, so they are 0 vectors. Okay, so this vector is actually 8 times 1, so 2 0 vectors of the same dimension. But the covariance matrix we need to compute, so because on the diagonal we already have covariance of v1 and covariance of v2. However, we need to compute B transpose, so here we will denote this B1, B2, B3, B4, okay, because we used C1, C2 here, so we'll use just B1, and when we multiply B transpose and C, we actually get that it is 0. So when we multiply this with this plus this with this, etc., we get 0. And our covariance matrix look like this. What does it mean for this one to be 0? Well, it means that they are independent. So V1 and V2 are independent. Also by this theorem. So use of this one is easy. Use of the theorem 7. Let's go to the following problem. So 6th in our case. And see how we can compute the maximum likelihood estimates when we are given a random sample. Okay, so we have 4 vectors that are distributed as a Bivariate normal distribution with given data in matrix X. So this is our matrix X, and using that one we need to estimate mu and sigma using the maximum likelihood estimate. Okay, so first, when we write it as x bar as a random variable, it is an estimator, and this is an estimate. So you can use this notation for either estimator or estimate, but if it is not obvious which one you use, you need to specify, but usually it is going to be obvious, as in this case. So we know how does the estimate, maximum likelihood estimate of the mean look like. So 1 divided by n, 4, times sum of our vectors xi. So our vectors are 3, 6, 4, 4, 5, 7, and 4, 7. And when we just substitute them, we know that the maximum likelihood estimate of our parameter mu is 4, 6. Similar, our maximum likelihood estimate, see it is small, our maximum likelihood estimate is given like this. So we need to compute all of those matrices and sum them, and in the end divide them by 4. So for example, because we needed to do it by hand, the first one, when we multiply, so x1 is 3, 6, our estimate of the mean is 4, 6, and then we need the same but transposed. So minus 1, 0 times minus 1, 0 transposed, we get this matrix. Similar we do for each of the 4, and we get this matrix for 1, 2, 3, and 4, and just divided by n. So it is also easy to compute the maximum likelihood estimate. But in this case, when we have a small sample, we can compute it by hand. However, when we have 100 or 100 variables, and 100 observations, it is really hard to compute it by hand. So there is softwares that can compute these estimates fast. The last problem for today will determine the distribution of something that we mentioned even earlier, also in theorems, which we just mentioned. They were not written in the notes, just mentioned in a video. Okay, so let's say that we have a random sample from multivariate normal distribution. So 20 random vectors with this distribution particular. So we want to know what is distribution of x1 minus mu transposed sigma to the power of minus 1 x1 minus mu. So it follows immediately from what we mentioned that it has a chi-square distribution, in this case with 6 degrees of freedom. This is theorem number 6, I think, in our lectures. So it follows immediately from that theorem, as it satisfies all the assumptions of the theorem. Next, we want to know what is distribution of our estimators. So our estimator x bar and another estimator given like this. Okay, so first we know that our x bar has this distribution. So we know that, but let's see. Expected value of our x, okay, is given like usual as we calculated, and it is mu. We already proved this part. Same with the covariance matrix, we proved it in one way, but we can also prove it in this way. So covariance of x bar, so we have just substituting x bar. This constant goes in front as squared because it is constant. So 1 divided by n squared, and then, because this is a random sample, covariance of a sum will be a sum of covariances, because a random sample means that the vectors are independent. So this equality holds, and just substituting sigma here and times sigma, we get this part. But we also proved this earlier. This is just a reminder. And what we want to know is distribution of this part. Okay, so as we have that x bar is normal distribution, we know that this y is going to have a normal distribution. Okay, so expected value of this, as the constant can go in front, and expected value of a constant is that constant. Okay, so we have just expected value of x bar, and this is mu, so mu minus mu is 0. Okay, and the covariance of this, of y, so constant goes in front, so we have it squared, and covariance of a random variable minus constant is just the covariance of that random variable, as the covariance of that constant is 0. So just by substituting we get sigma. So our y has this distribution. You can also notice that this is a part of a central limit theorem given in the literature. And in the end, as we already know what is the distribution of n minus 1s, so it is a Wichern distribution with n minus 1 degrees of freedom. If we are given a sample of 20, as in our case, we know that n minus 1, so 20 minus 1s has, so this random variable has a Wichern distribution with 19 degrees of freedom, which follows from the theorem that we mentioned. And the last problem is going to be computed in Excel in the following video. So this will be it for this video. Bye.